Okay, so our heading is Electrochem, electron transfer. Again, this is a 30% unit, and the first chapter is chapter 13, which is all the new information that you need. The second chapter, chapter 14, is all the applications. Voltaic cells, which are batteries, and electrolytic cells are kind of like batteries, but they don't happen on their own. We have to force them to happen. Okay. So this is my intro slide to work our way into the oxidation and reduction key terms in this lesson. So we're going to take a look at a reaction. This is one of the reaction types from way back in Science 10. This is a single replacement. Okay? And a single replacement reaction is an example of electron transfer reaction. We just never talked about it in Science 10 being a electron transfer one. To study whether something has electron transfer and is electrochemistry, we need to track electrons. So that's the first thing I'm going to do. I'm going to look up how many electrons each species has. Okay? Now to do that, I'm flipping to the data booklet and looking up that atomic symbol. Okay? So the very first thing we have is zinc, zinc solid. Right? You don't have to write this in, but you have to realize that is neutral, has no charge. And if I look up zinc in your data booklet, zinc has 30 electrons. Okay? Now what I'm going to do is put the total electrons on the bottom, and on the top I'm just going to write the charge. Okay? And in future examples I'm just going to do one of these two methods, but I want to give you the visual of the total electrons and how charge is a shortcut. Okay, so zinc has 30 electrons, has no charge. If we look at HCl, okay, that HCl is a compound that is pretty close to being ionic, and I'm going to treat it ionic as that H being a 1 plus, and a chloride 1 minus. If you think of H plus, well, hydrogen by itself would have 1 electron, but as H plus, it has 0. If we look at that chloride, that's Cl minus, chlorine is atomic number 17, and minus, it would have 1 extra electron, so it'd have 18. Okay. Now there is a 2 in front. All of the charges and the electron counts that I'm writing is just for one of the atom or the ion. So we've got a zinc with 30 electrons, we've got an H, we happen to have 2 of them, they both have none, and we have 2 Cl minuses, and they're both 18. Okay, now we're going to do the same thing for the other side. When we get to the other side, I see zinc again, but it's no longer zinc neutral. Okay? We now have zinc in an ionic compound. Okay? That zinc is the 2 plus type. Okay? Now one way you could get that charge is to look up chloride's charge and figure out what zinc's would be, or if you look in your data booklet, the only possible charge for zinc is plus 2. Okay? So when I say your data booklet, I'm looking at just the inside of the front cover. It would be the very first page. So that zinc is plus 2, so it no longer has 30 electrons, it's down to 28. Yes, the plus 2 type. Okay. Next we got Cl. That's a Cl in an ionic compound again. That's not diatomic chlorine, that's an ionic compound, 1 zinc, 2 chlorides. Well, that's exactly the same as before. We had a chloride back with a hydrogen in the beginning, and we have a 1 minus Cl, and each of those have 18 electrons. Okay. Again, I know there's 2 Cl's, each has 18. It's not 18 in total. Okay. Last, we have hydrogen. Now, all molecules have no charge overall. Okay. In terms of electrons, I've been writing the electron count for each H. Here we've got 2 of them. So, you know, H2 looks like that, Chem 20 bonding lines, if I did an electron dot diagram. Okay. That hydrogen has hydrogen molecule has 2 electrons. Now I've been writing the electron count for one of all of the atoms or ions, so I'm just going to, there's 2 electrons and there's 2 H's, so I'm going to divide that by 2. There's 1 electron for every H. Okay. So we start with zinc with 30 electrons, reacting with a hydrogen with none, a chloride with 18, making a zinc with a 28, a Cl with 18, and makes diatomic hydrogen with 1 electron each. Okay. And now we can finally get at what's going on in terms of electrochemistry. So we're looking for changes. If I start with my zinc, that definitely changed. It went from 30 electrons at the beginning down to 28. I did that arrow a little further than I wanted. There we go, zinc to zinc. We start with 30, we end up with 28. There is a loss. I'm going to go minus 2 electrons with that zinc to go from 30 down to 28. Okay. Now in a reaction, we're going to see that whenever you have a loss of electrons somewhere, you have to have a gain of electrons somewhere else. So somewhere electrons were gained, and that is with our hydrogen. Every hydrogen starts with 0, and they end up with 1 on the product side. So there's a gain, so I'm going to write plus 1 electron with the hydrogen. Okay. Now, just to be super clear, I'm going to put in or highlight minus 2 electrons for every zinc. So I'm just going per zinc or slash zinc. With the green, it's plus 1 electron per every H. There's 2 H's, so in total there will be 2 electrons transferred. Okay. But it's 1 electron each. Okay. Now you can track electrons like I did on the bottom using the total count, but it's much faster and you get the same answer if you just look at the charge. Okay. So if you look at the hydrogen going from plus 1 to 0, okay, you get the same type of trend. Okay. So we've tracked the absolute change in each molecule. What has happened? Okay. 2 big things have happened. Zinc lost 2 electrons to become zinc 2+ ion. That was one. That was the red. The other key piece is 2 H pluses gain 2 electrons, 1 each, to form molecular hydrogen. Those are that's our gain and our loss, and we always have to have this pairing. Okay. Now there's one other atom that never showed up in the so what happened statement, and that is Cl-. Okay. Cl- didn't do anything. It started with 18, it ended with 18, so it's just a spectator ion. Okay. There's no electrochemistry. There's no gain or loss of electrons with our chloride. Okay. So the point of this slide was to find the 2 pieces, the gaining and losing of electrons, and now I want to talk about, well, there are distinctive names given to these names. First, key fundamental definition. Okay. This unit is largely a terms, definition, understanding type of unit. There is some math and calculations, but it's not a calculation-heavy unit. It's more of a theory-heavy unit. So reduction, that by definition is a process where there is a gaining of electrons. And in the example we just did, what gained electrons was the H+. When you gain electrons, your charge goes down because electrons are negative. The second key definition is oxidation. which is the loss of electrons in the process that involves the loss of electrons. Okay? In our example, that was the zinc metal, started with 30 electrons and lost 2. Okay. Okay. I'm going to highlight, and that's going to be the theme for the rest of this this first lesson. Okay? When you put the two together, reduction and oxidation, you get a redox reaction, a reduction-oxidation reaction. Redox, the RE from reduction, sorry, the RED from reduction, and the OX from oxidation. That's where the word redox comes from. Okay? You must have something losing and something gaining. Not all chemical reactions are redox, and that's something we'll address in a future lesson, which type of reactions are redox and which ones aren't. Okay? We just saw a single replacement reaction, and all single replacements are redox. So redox reactions are chemical reactions where electrons are transferred from one of the reactants to another one of the reactants. Okay. In studying redox reactions, and this is how your data table on page 7 is built, is by studying half reactions. They're a balanced chemical reaction that shows either the gaining or the loss of electrons. Okay. It doesn't show both. Okay, showing both would be a redox reaction. Showing just one of the two halves, one of the two pieces, the gaining or losing, we call them half reactions, and we're going to be writing lots of those. And we're going to take a look at half reactions on the bottom of this slide. So I'm going to put back up that reaction that we looked at on the previous slide, and we're going to write out the two pieces next. So I'm going to start with the oxidation. So the oxidation, our new definition is that is the loss of electrons or the process that lost them. So the loss was our zinc. Our zinc started with 30 electrons and ended up with 28. So we only need to show those red underlined pieces in the oxidation half reaction. So I've pulled down those red underlined pieces. Okay. So zinc solid is our only reactant in the oxidation half reaction. Producing the only product is zinc 2+, but then we've got to show the electrons that aren't shown in the single replacement. Okay. Zinc going from neutral up to 2+ involves losing 2 electrons. Anytime electrons are lost, they're going to be a product. Anytime there's a gain of electrons, they're going to be a reactant. Okay? So I'm writing the oxidation. Electrons are lost here. They're going to have to show up on the product side. Our other half reaction involves our 2 H pluses producing elemental hydrogen. So that's what we see in the reduction half reaction. I've pulled down the 2 H pluses. It requires the gaining of 2 electrons, and we get our elemental hydrogen. And I'm not going to write it out. If we netted these two reactions together, we would get the net redox reaction. Or actually, I will write that out just so you can see it. When we write redox reactions, as you've been doing for years of single replacement and not even realizing it, you never wrote the electrons in. They always canceled each other out. Okay? We have 2 electrons from the oxidation, and they're going to cancel out the 2 electrons from the reduction. So we don't see them in the net. We just see the zinc that loses electrons, the 2H plus that gain them. We get the our ionic zinc with the zinc after it's lost electrons, and we get the 2 H's molecularly bonded to each other when they've gained. 2. Now you'll notice in the net reaction, there is no chloride showing up. Spectator ions disappear when you put two half reactions together, okay? Because spectator ions aren't going to show up in either half reaction. Okay. So we saw an example which led to our definitions of oxidation reduction. Next is a mnemonic. How are you going to remember this oxidation reduction? You just need to remember that Leo the lion says grr, and you'll be fine. So Leo helps me remember the oxidation part. Grr, gaining electrons reduced. That helps me keep track that reduction is the gaining part. Oxidation is the losing. Now, with lots of practice, you'll stop maybe saying Leo and grr. I'm going to write Leo and grr all through my notes as a reminder for you. Okay? It's not something you have to know. It's not something you have to memorize. It's just a mnemonic. Okay? So I'm going to do a couple more examples, give you some skills or tools, talk about your data table and how that can help you, and then you're going to be ripping net reactions apart and figuring out what's the oxidation, what's the reduction. So for the last example of this intro lesson, we're going to break apart, understand the reaction of copper metal with silver nitrate. And I want to do a couple things. I want to write out two balanced half reactions, so an oxidation and a reduction, and I want to write out a balanced net equation. Okay. Now that net won't have any spectator ions in it. Okay. So I have to go back to my Science 10 reaction type skills and think of which reaction type is this, because I didn't list the products for you. Now we do have the reactants in words. Copper metal, that's a metal by itself. Okay. All metals except for mercury are solid at room temperature, so that's where the solid came from. And metals by themselves are neutral. Okay. You don't have to write in the zero charge. I actually would like you to write in the zero, because a lot of students like to always write charges in with metals, but when they're by themselves, a metal has no charge. Okay. When it's in an ionic compound, it does have a charge. So that's our copper part taken care of. That the second chemical is silver nitrate. Silver in your data table is +1. Nitrate is a polyatomic ion, which is -1, so we just need one of each of those. So that's why I wrote 1 silver and 1 nitrate. Not putting the ones in. Okay. Now I've got to predict the products before I can do any redox analysis. Any thoughts? What type of reaction do I have here? I need to realize that in order to get products. So there's 5 reaction types were combustion, single replacement, double replacement, decomposition, and formation, and it is a single replacement. Okay? So that's what I have to keep in mind. So in single replacement, the metals are going to switch places, and we have to, think of their charges. So the copper is going to pair up with the nitrate now when it switches places with the silver. And then the silver is going to end up all by itself. Okay. Now that copper isn't done, I have to figure out what charge that copper is, and that will then tell me how many nitrates I need. So this is where I need to go to my data table right inside the first cover and look up what is the most common charge for copper. Hopefully somebody has their data booklet. What is the most common charge for copper? And it is +2. It is 2 types, but the +2 is written first. So this is +2 copper. This is 1 minus nitrate, so to make this balance, I need 2 of those. So now I've got the products out. I just need to balance this whole thing, and then I can start trying to figure out what's going on redox-wise. I got 1 copper at the beginning, 1 copper at the end, 1 silver at the beginning, 1 silver at the end, 1 nitrate at the beginning, 2 nitrates at the end. So to fix my nitrate, I have to put a 2 in front of my silver nitrate. That doubled my silver. I double my silver at the end, and now I've got my balanced equation. So now I'm going to start diving into part A. Let's start trying to figure out what was oxidized and what was reduced. So what was oxidized? And our mnemonic, to remember that, is losing electrons is oxidized. I'm going to throw in some charges. That is silver 1 plus. We got nitrate, a polyatomic ion. I won't dive into all those pieces yet. And I'll just label this as neutral silver as our product. Okay. The NO3 doesn't change at all. And when we see something not changing the charge or the count of atoms in an ion, there's going to be no electrochemistry there. If we look at, so what lost electrons? Copper started with 0 and ends up +2. 0 to +2, that would be losing electrons. You have to lose 2 electrons to end up positive. So what was oxidized? That is our solid copper reactant. Okay, so we're going to have to write a half reaction with just the copper. What was reduced? So that's our GR. What gained electrons? That's going to be our silver. It goes from +1 and it goes down to 0. Okay, it gains 1 electron. Okay. Now again, all these numbers are 2 electrons per copper and 1 electron per silver. Okay. So what was reduced? Which reactant was it? It's the silver plus. Okay. I'm not going to include the nitrate. It's just the silver that gained electrons. Okay. So now I can write a couple half reactions knowing what was oxidized and what was reduced. So I'll start with the Leo. So the oxidation, which always has the electrons as a product. We had solid copper becoming copper 2 plus, and there's a difference of 2 electrons there. Our reduction, our GR, gaining electrons reduced, so this better have electrons at the beginning. We have silver, and that's silver plus, and that picks up 1 electron, it gains 1, and then we get neutral silver. You don't have to put the 0 charge in, but I really encourage you to put those in. So that's part A done. We figured out the oxidation, we figured out the gaining. Okay. Last, B, what is the net? Well, to get a net redox reaction, you have to put 2 half reactions together. So we're going to add the 2 half reactions, but we do have to balance the electrons before we do it. Okay. When we look at these 2 half reactions, I've got 2 electrons in the first half reaction, and I only have 1 in the second. Okay. When we write half reactions, they're always written with the lowest possible coefficients. That's how half reactions on page 7 are constructed, and that's how you're going to learn to construct them. When we net reactions up, we often have to multiply 1 or both reactions to find the lowest common multiple of electrons. In this case, the lowest common multiple between 2 from the copper and 1 from the silver is 2 electrons. I have 2 electrons in the top. I have to double the bottom reaction to get 2. So I need 2 silver plus and 2 electrons producing 2 neutral silver. Okay. The half reaction is the black. The blue that I put over top of it is manipulating it to build the net. And that leads to me being able to cancel my electrons to build my net. And I end up with copper solid plus 2 silver plus producing copper 2 plus and neutral silver. And our spectator ion of nitrate disappeared because it's not involved in any electron exchange. What we're seeing here is the heart of batteries, and that's what we'll look at in chapter 14. If you separate these two chemicals and make the electrons not go from chemical to chemical in solution, but run through a wire, you can power your iPhone, you can power any electrical device you want, and in today's world, you can power an electric vehicle with the electron flow. Okay. So a few skills, tools for you, and then you're going to be practicing in a couple minutes. So the first big tool I was using and talking about is this your data table. Okay, you're going to be flipping through this all the time. In single replacement reactions, like we just saw, you'd have to be looking for copper to find out what is the most common charge. Okay. Now your group 1 and 2 metals are a bit simpler. All the group 1s are 1 plus, and all the group 2 metals are 2 plus when they're ionic. Okay. When they're by themselves, they are neutral. If you have sodium all by itself, it's not +1, it's neutral. It's only when you have sodium with something else that you have it as a charged species. Okay. So to get charges that aren't listed in questions, you're expected to go to your table. You're going to see lots of polyatomics again, like nitrate that we just saw, and those names are all in that table. Okay. So that's the first tool that's really useful, essential for you to be looking up those charges. The second key tool, this is really blurry, but this is your data table from page 7. This is a table filled with reduction half reactions, and you're always going to have this table on tests and exams. Okay? So when you're back, when we're doing our first quiz or our unit test at the end, this is there for you, and you'll see if you look in your table, that whole silver half reaction is right there in your table, and that copper half reaction we're just looking at is in the table, but your table has them all written as reductions. Okay, your table is built as a GER table, a gaining table where all the electrons are on the reactant side. Okay? And we'll talk even more about this table in lesson 2. The last thing I'll just highlight, if you think of the forward direction of this table, it is a reduction. If you go backwards, okay, so if you think of starting with copper and going backwards, that is an oxidation. Okay? So it's a reduction table, but you can get oxidations by working backwards.